Good afternoon, everyone. Today, the Atom Seminar has the great pleasure to welcome Professor Sepideh Razavi. Professor Razavi is an assistant professor of chemical engineering at the University of Oklahoma. She received her PhD degree in chemical engineering from the City College of New York, and then she worked as postdoctoral researcher at the University of Michigan. Professor Razavi has been awarded with the Doctoral New Investigator Award of the American Chemical Society in 2020 and with the Career Award of the National Science Foundation 2022. Her research focuses on fundamental studies of the interaction of colloidal particles with liquid interfaces, with emphasis on anisotropic particles, using experimentation and simulation techniques. So once again, welcome, Professor Razavi. Thank you so much for being here, and please feel free to share your screen and start your presentation.
Okay, thank you so much for the invitation. I'm excited to be here and talk to you about some of the work my group has been doing on multi-component fluids near interfaces. Before I start, I thought the intro put it already there, but I wanted to kind of put it on the map where my background is and where I come from. I got my degrees all the way to master's from Iran. After getting a master's degree at Sharif University, I moved to the US to pursue PhD. As you can see, I moved to the East Coast, did a PhD with Ilona Kretschmar, and then I moved to Michigan to do a postdoc in the lab of Michael Solomon. I was there from 15 to 18, and then starting in 2018, I moved to University of Oklahoma, where I'm an assistant professor here. So as you can see, I've lived on the East Coast, in the Midwest, and now I'm in the Heartland. So my lab does work on colloids and interfaces, and we are interested in understanding how we can build on the knowledge available on isotropic and ideal particles and move towards particles that are heterogeneous, anisotropic, and more importantly, more technologically relevant. So as you can see here, we work on a phase space, which is pretty broad, looking at particle roughness, effect of shape anisotropy, surface anisotropic particles, combination of these factors, and again, to think about more technologically relevant systems, we also look at mixed systems where we have surfactants and particles, because oftentimes in formulations or in industries, you deal with systems where both of these species are present. So while we're a fundamental group, the kind of problems we work on have applications in addressing challenges related to energy, environment, and sustainability. So in the next few slides, what I'm going to show you is kind of a broad picture of what applications our research could be useful for, again, under the umbrella of energy, environment, and sustainability. And then after that, I'm going to focus on the case of Pickering Foams. Okay, so bear with me if this is something that you do work on a daily basis. This is just meant to be for a general audience, these first introductory slides. Okay, so energy and water, they are highly interrelated. We use water for subsurface energy recovery, for mining, for thermoelectric power generation. As you can see, a large portion of water goes into thermoelectric power. And on the other hand, energy then is used to clean water, to pump water from aquifers for agricultural purposes, and so on. So these are highly interconnected. And with the growth in the human population, as you can see here, by the year 2050, it's projected that the demand on energy, water, and food is going to continue to grow. On the other hand, we also know that kind of looking at conventional ways of producing energy and consuming water, we cannot keep doing what we have been doing the old ways, because that's not sustainable. So you're looking at, for example, a number of sustainable development goals. That is an urgent call for action to all countries, right, in order to ensure prosperity and a peace of human and planet, not only for current generation, but future generations. So out of the 17 Sustainable Development Goals, I'm putting out 4 here. As you can see, there is connection to water and energy. So the problem is that the population is going to continue to grow. And if we want to kind of stick with the production of energy using fossil fuels, we're going to generate greenhouse gases, which is going to lead to exacerbation of the climate change, right? So in order to then come up with solutions that can address this issue, we have to have all hands on deck, not only on the production, but also on the storage. Renewables are great. We can use renewable resources because they're readily available to produce energy, but the issue with them is intermittency, seasonal dependence, and the fact that they're not necessarily go hand in hand with the demand. So if the sun is shining or the wind blowing, that's great, you can get renewables, but if that's not the case, then your energy production is going to go down. So hydrogen is coming out as emerging as a very promising alternative for energy storage, where you can basically use renewables to produce energy and then store it in hydrogen, and then kind of use hydrogen to balance this control on this demand and production of energy. Okay, so production of hydrogen is not something that's been new. It's been around for decades, where fossil fuels are used for methane steam reforming. Now, the problem with this production is, again, the production of greenhouse gases. If we use renewables to then use water and go through electrolysis of water to produce hydrogen, we can get around producing the greenhouse gas emissions, okay? Well, what is the importance of interfacial phenomena and all of this I'm talking about? Well, the fact is that we need to have high capacity for storage to store this hydrogen that's being produced through electrolysis in order to be using it on demand, right? When the wind is not blowing or the sun is not shining. And depleted oil and gas reservoirs, they have been emerging as a great potential for storage of hydrogen because, for number one, they have been holding hydrocarbon for millennia. Oftentimes in these depleted oil and gas reservoirs, there's already infrastructure for charge and discharge, so that can benefit economically. And therefore, these can be great because they also offer very high storage capacity. However, there's a lot of fundamental questions that needs to be addressed before this vision can be realized, and that's where our understanding of interfacial phenomena can be very useful. If you look at the close-up of some of these sample, for example, reservoir rock on the bottom, you can see that there's a very large compositional heterogeneity in the sample that is shown in these different colors. And therefore, in order to, for example, store hydrogen-bearing fluids, one has to understand how this fluid is going to wet and spread on this surface that is very heterogeneous in terms of its properties, right? So how does the hydrogen interact with the surface? How does it spread? What are the potential reactions that could occur, and so on and so forth? So this is an example of where fundamental interfacial phenomena questions can be used to address bigger issues and challenges on the intersection of energy. But as I told you, energy and water are related, right? So if you're talking about electrolysis, for example, to produce hydrogen, that is going to require a large quantity of water. For every kilogram of hydrogen, you would need 9 kilograms of water. And if you also consider how much water you would need for cooling of a power plant, for example, if you were to use the hydrogen for in a power plant, that could add up to 15 to 20 kilograms of water. So that's a large quantity of water, especially if you're going to use this method in a very water scarce area. So now, basically wastewater is being used as a resource. Can we use wastewater that is available to be able to then use that as a resource for electrolysis to produce hydrogen? Again, another opportunity for us to come in and kind of fill in this gap, because if you're now thinking about wastewater, you're working with a soup of many different ingredients, such as ions, heavy metals, surfactants, polymers, nanoparticles, what have you. And you have to understand how these different species interact with each other. How do they interact with surfaces? For example, if you were to use membranes for separation, how can you selectively prevent or promote adsorption of a species? How would they lead to fouling? How could you prevent fouling? So these are all issues that can be addressed using interfacial phenomena and colloid science. Again, water and energy highly interrelated, right? So you're talking about water and wastewater. One of the avenues where wastewater is a major problem is subsurface energy recovery. So when we want to get oil out of the reservoir, Oftentimes water flooding is being done, where water in conjunction with additives such as surfactants that are used to reduce the surface tension and help with the mobility of oil, and particles that are used as proppants are added. And then once the oil is removed on the other side, the water is going to come out with all these additives, surfactants, particles, and therefore this produced water has to be dealt with. And this is a large quantities of water we're talking about 21 billion barrels in the US. And as you can see here, Texas, California, and Oklahoma are the 3 largest contributors to this produced water annually in the US. Oftentimes this is just discharged in the ground, but as we know, these mismanaged waters can have issues for the environment. So not only we are talking about very large quantities of water that can again strain areas that are water scarce, but also mishandling of this water is shown to affect the diversity and function of microbes. It is shown to basically affect the quality of the water that can be used for irrigation or human supply. It can leak into fresh water and groundwater surfaces, and therefore it's going to be problematic. Any effort we could put into diminishing the use of water in subsurface energy recovery could be very beneficial to not only how much water is going to be saved, but also to the environment. So foams are a potential alternative in this case, that they can cut back on the water usage in subsurface energy recovery by 90%. They're great because of their stability, their biocompatibility, and environmentally friendliness. So there are a lot of good things about using foams. But again, where we come in as a group that does fundamental interfacial science is understanding how this multi-phase fluidic system is going to interact with surfaces. How does its stability changes as you change the surfactant or particle concentration? And how can we basically engineer this soft material, foams, in order to have a specific function depending on the properties of the environment we are working with, such as pH, for example, and salt conditions. Okay, so with that kind of intro into different areas of energy sustainability and water, where our fundamental research could be very useful, for the rest of the talk, I'm going to just focus on these Pickering foams and what we have done to understand their properties, okay? Pickering foams, or foams in general, are a system of dispersed bubbles in a continuous fluid phase, as you can see here. And because of their very high surface area, they're going to be phase separating over time and through bubble coarsening. So as you look at this video, these small bubbles are getting smaller and smaller because the gas is diffusing from the smaller bubbles due to their larger Laplace pressure, and it's diffusing towards the larger bubbles. And this is going to keep continuing until the small bubbles pretty much disappear. The bubbles can also coalesce, and that's another mode of coarsening. And this takes place, if you kind of look at these 2 bubbles here, by thinning of this liquid film, draining of the liquid film, and eventually snapping of that film that give rise to these 2 bubbles coming together and coalescing and coarsening. And all throughout these processes, a foam column is also going to undergo liquid drainage under the effect of gravity, as you can see here. The water is going to drain to the bottom, and you end up with a more dry foam on the top and more wet foam on the bottom. So in all of these cases, as you can see, I'm talking about the flow of fluid as well. So it's important to understand how this liquid film is going to move. And therefore, understanding what's happening at these interfaces is crucial to determining the flow of fluid, because the properties of that interface and its response to flow, in other words, its rheology, is going to set the local fluid velocity close to that boundary. And that's what we set to do, to really understand what is happening at these interfaces as a function of different stabilizers. Well, usually surfactants are used to stabilize interfaces, and as you all know, they reduce the free energy of the system by reducing the surface tension. So here's the case of STS, where by increasing the concentration of surfactant, you can reduce the surface tension up to the critical micelle concentration. For a lot of the applications involving high temperatures, high salinity, there are issues with just using surfactants because of their precipitation and their degradation and instability. And particles are great choices in those cases. And with the use of particles, the reduction in the free energy is not necessarily associated with surface tension, but rather the particle will sit at the interface, and it's going to block these two faces from seeing each other. And therefore, by removing this contact area, which is highly energetically unfavorable, they're going to lead to lower free energy of the system. So therefore, by changing the particle size, you can change that contact area that's being removed, but also by changing the wettability of the particle, you can change how high the particle is sitting at the interface, and therefore you can affect the energy removed that way as well. So it's not surprising then the binding energy of a particle is going to be related to its size and its contact angle. So for example, if you have a 250 nanometer particle that is neutrally wetting, which means that sitting halfway through the oil water or air water, you can come up with a binding energy that is about 1,000,000 times kT, where kT in this case is the scale of thermal energy. So if you think about it now, you have this system where the particles are bound to the interface with a very high energy. So you can think about it as irreversible adsorption. So these particles bind to the interface and they're not going to pop out of the interface unless there's some applied deformation, as you'll see throughout this talk. Okay, so again, if you're mainly working with surfactants, I'm going to just give you a range of this colloidal domain of particles we work with. So they're definitely bigger than the molecules, and they're smaller than granular matter. You can think about the sand at the beach for the granule size. And we work with particles that are tens of nanometer up to a few micron. And the important features of colloidal particles is their Brownian motion first, which is basically bombardment of these colloids by the molecules of the solvent that lead to this random motion of the particles, and also their arrangement and self-assembly as the interaction potential is going to be altered. So you can play around now with the properties of the particles, their surface properties, their shape, in order to then play around with this interaction potential, then affect the microstructure that is forming and their self-assembly. So what we do in my group, again, we work on understanding how these features can affect the interaction potential that then can be used to tune the interfacial systems and their properties, but we want to understand what is happening at these interfaces. Can we engineer these systems from our understanding of interfacial properties? Can we tune the interaction potential by changing the properties of the particles, and then look at how the microstructure is going to be impacted by that? And then can we understand how those microstructure are going to lead to special properties of these emulsions and foams by our understanding of the rheology at the interface, basically how they would deform under applied deformations, both in dilation and shear. So we work on pretty much many different attributes of particles, but today I'm going to just focus on particle wettability and particle roughness for this talk. Okay, so the system of interest are silica particles. They are 250 nanometer in size. As you can see here, an SEM image of these particles, and here's more close-up electron microscope of these particles. We put them in water, we sonicate them, make a dispersion, and then we put them in this dynamic foam analyzer, which we basically sparge the gas from the bottom through a glass slit, and then have these bubbles basically go through the dispersion to make a foam. This is the work that my former graduate student, Nick Brown, did. And when he first tried these silica particles, we weren't able to make any foam, as you can see here. Then what we did was we hydrophobically modified these particles because, as you know, silica particles suspended in water are going to be negatively charged. So what we did was replace some of those silanol groups with methyl groups through silane reaction. And then we repeated this experiment to make a foam. As you can see on the right-hand side, now we have hydrophobically modified silica particles, which we were able to then generate a whole lot of foam with compared to the case of unmodified silica particles. So we wanted to understand what is happening at those bubble surfaces that only by changing the wettability, we are dramatically changing the amount of foam that can be made. So we go back to interfacial techniques and tools that we have in my lab. The first one is a Langmuir trough that is conventionally used for studying surfactant adsorption to fluid interfaces. It's basically a Teflon trough. You fill it up with the subphase of interest, in this case, water, and then you deposit your particles at the interface using a spreading solution. Here you're looking at a film of particles. There is a Wilhelmy plate that can help you understand what is the pressure at the interface. which is an indication of the interactions between the particles. You can think about it as surface tension of air-water interface that's clean, minus the effective surface tension in presence of the particles. So that is basically the pressure that is coming about due to these particles interacting. And in order to play around with the coverage of particles, we have these two barriers that can help us compress the interface to effectively increase the surface coverage of the particles at the interface. As we're all doing all of this, we also have integrated this system with an inverted microscope, as you can see here, so we can look at what is happening to this interface and what kind of microstructural changes are going to result as we compress this network using this microscope. The kind of data you get is then the pressure area isotherm. Again, this is very straightforward for surfactant systems, now adopted to particle systems. At the beginning of the experiments, if you're at a very low area fraction, the pressure is 0, meaning that the particles are not interacting. As you start compressing, you're effectively increasing the surface coverage of particles, and they start to interact, so the pressure goes up. And then at some point, if you keep compressing, you're going to jam the interface, and you're going to saturate basically the space available in 2D, and the network has to respond to those deformation. It's going to collapse, which is known by this shoulder in the pressure area isotherm. So very similar to 3D, where you can think about how much pressure do I need to apply to obtain a certain change in the volume in a piston and cylinder system to get the bulk modulus. You can also get an isotherm compressional modulus for these 2D systems by looking at the slope of these isotherms. It's basically a resistance of the network to applied compressions and how much it resists to applied compressions. Okay, so going back to this system of hydrophilic silica particles versus hydrophobic silica particles, now studying their behavior at the interface. So the first thing we did, we put these kind of more hydrophilic silica particles at the interface, and we are compressing from right and left to the center of the screen. And as you can see here, after the particles saturated the space available in 2D, they're going to get removed from the interface and get expelled into the subphase because we keep compressing and we are pushing them. These are negatively charged. They are interacting through Coulombing interactions through the water phase. So they would rather go to the subphase because the repulsive interactions are really high. So this explains why we are not able to trap as many bubbles and stabilize foams using these hydrophilic particles. Then once we move to hydrophobically modified particles, we again repeat these experiments looking at their properties at the interface, and here is the response you're going to get. Well, first of all, you see that the particles are coming out darker, meaning that they're poking more in the air phase, which makes sense because they're hydrophobic. And once we start compressing and everything in 2D is already saturated, the particles don't leave the interface. They actually rather form this elastic sheet that can wrinkle and fold. And it's a very reversible process that you can compress and expand. The particles will not leave the interface. And again, this explained why we were able to then stabilize these bubbles using these particles, because as the bubbles say coarsen or shrink, these particles are not going to leave the interface in response to those applied deformations. So kind of the message here is that the wettability is important for stabilizing these particles at the interface, and also the response of the network to applied compression. So the particles have to be slightly hydrophobic. If they're too hydrophilic, they're going to get removed from the interface under applied deformations. Once we have an understanding of the degree of hydrophobicity we need, then we moved on the understanding what is the effect of the surface roughness of the particles. So these are, again, the hydrophobically modified round silica particles. Now we also have another set of particles where instead of being isotropic and ideal and round, these particles are made from individual nanometer-sized silica particles that are fused together, so they're more aggregate-like. They're known as fumed silica particles. And we choose them so that they have a similar hydrodynamic radius in bulk. So even though these are not round, at least in the bulk, they have a similar hydrodynamic radius to these round particles. And as you can see, if you make a monolayer of these particles and look at a contact angle of water on the surface to get an idea, an approximate estimation for the contact angle, we'll see that these are hydrophobically modified. And as we increase the roughness of the particles, it's also known that the contact angle is going to go up. So you have a more hydrophobic surface, if you will, because of the roughness of the substrate. So once we have these two, we're going to go back to the dynamic foam analyzer, and very standard way of looking at these foams is just look at the foam height and the total height. And you can do that by just having a light source going through the foam, and then on the other side, having a sensor to capture how much light passed through. And then from there, you can say how much is the foam height and how much is the liquid height, and then how it's changing as a function of time to get the foam stability and aging. Okay, so here's the data for the foam, for the total height of the foam we make using both type of particles, round particles and rough particles. And we also, as a control, have the SDS stabilized foam systems in black to just look at how better the particles are doing compared to a surfactant stabilized system. So as you can see here, the two particle types are very stable compared to the SDS stabilized system over the course of an hour. And if you also normalize all of this axis, the y-axis, with the initial height of the system, the foam that we have made, what you can see again is that the particle stabilized systems are pretty steady, whereas the surfactant stabilized one is coarsening and it's dropping in terms of the height that it has over time. Okay, so what is happening and how can we explain this from understanding the interfacial microstructure of these bubbles? We can further characterize these systems by looking at another set of light source and a sensor. This is a light source that is coming through in the back of this foam column right here. There's a prism that you can shine the light, and either it can go through the solution or it can get diffracted from the bubble surface and get picked up by this objective to give you these bubble microstructure data as well. And we have this camera on a railing, so we can actually move it up and down to get microstructural information as a function of the foam height. Okay, so here is the information on the microstructure now. If I looked at the three systems of the particle stabilized foam and the surfactant stabilized foam. So as you can see here, even though the surfactant stabilized bubbles are much smaller to begin with, they coarsen so much over the course of an hour that eventually they're going to destabilize and give rise to a smaller and smaller foam height. Whereas the particle stabilized ones, even though they started to be larger bubbles, they're pretty consistent over the course of an hour. Okay, well, how can we explain this from the properties of these particles we have put at the interface? Well, if we look at the kind of driving force for coarsening, the Laplace pressure can be written as 2 gamma over r, and gamma is surface tension, r is the radius of the bubbles you're looking at. And if the network at the interface doesn't have any compression elasticity, the driving force again is this delta P. And as the radius of the bubble is changing, so look at how this driving force is changing as the bubble is coarsening or shrinking by just differentiating that as the R size of the bubbles are changing. What you will see is that the change in the delta P as the bubble size is changing is negative, just because gamma and R squared are always positive numbers. So this negative sign is going to lead to this ratio being always negative. So what is that telling us is that as the bubble keeps coarsening, in the absence of any compression elasticity, this driving force is going to be there, and it gets even exacerbated further and further. And that's why the smaller bubbles shrinking and the larger ones keep getting bigger. However, this scenario can be reversed if you have an interface that has some compressional elasticity and rigidity at the interface that could balance this driving force. So if you have a mechanical rigidity or elasticity kappa S that is greater than half of the surface tension, you can actually arrest this diffusion of gas from smaller bubbles to larger bubbles. And this is known as the Gibbs elasticity criterion. So we wanted to then go back to these networks of particles we have formed and see whether this condition is satisfied or not. Okay. So how do we do that? This is the work of my Dr. Elton Correa, who was my graduate student that just defended his PhD, and also he is an alumnus of your institution as well. So he basically put these particles at the interface, both the round ones and the rough ones, and he looked at the surface pressure versus area isotherm for these particles to look at what we can learn about the interactions of these particles at the interface and eventually their compressional elasticity and mechanical stability. So again, the goal is to kind of relate back to this Gibbs elasticity criterion. What you can see here is that both of the particles are trapped pretty well at the interface because, again, they're hydrophobically modified. What you note here is that these rough particles, the surface pressure starts to pick up earlier on compared to these round particles. So somehow the interactions between these rough particles is longer range, so they start interacting over a longer distance. And eventually they both form these wrinkles and folds. They behave like an elastic sheet, again, because of their hydrophobic modification. So you can think about this long-range interactions and the reason for this network of these fumed silica particles start to form a network earlier on in terms of capillary interactions. And you have seen that in your cereal bowls as a Cheerio effect. Or so if you have looked at the Cheerio beads here, what you see is that because they deform the contact line around each Cheerio, then the two Cheerios are going to kind of interact with each other and attract each other to remove that interfacial deformation, which is, again, highly energetically unfavorable. So similar ideas here at just much smaller scale. Okay, so capillary interactions are important in making these networks at the interface. So once we have the network, again, we want to understand what is its mechanical stability. We use a drop-shape tensiometry to put these droplets at the interface, put the network at the interface, and look at the surface tension, just using Young-Laplace equation. Once we have the particle network at the interface, what we can do is we can pulsate this network. So we want to understand what is the mechanical properties of this network, and we can obtain this information by perturbing the network, right? So we change the volume of the droplet, which is going to translate into the change of the interfacial area, here shown in the red. And once the area is changing, the effective surface tension is going to change in response to that applied change or applied deformation. And again, as you know, if these changes or if the response to the applied change is completely in phase, you have a very elastic network. And depending on the phase shift between the applied change in the area and the response of the effective surface tension, you might have a viscoelastic network. So with these experiments, then we can get the mechanical properties of the network, which is what we are after, to go back to that Gibbs elasticity criterion, as a function of the surface coverage. Because what we can do is we can compress the network, we can basically decrease the volume and effectively increase the surface coverage at the interface. So as we decrease the area, we are effectively increasing the particle coverage at the interface. So as you can see, both of the two particle systems have a very high elasticity. And after we have reached the maximum packing, they're going to buckle, and that's when you see the elasticity go down, because now they have released the stress by wrinkle and buckle formation. Now, if you compare this to the case of surfactants, where we can also do similar experiments as a function of surfactant concentration, they are an order of magnitude smaller in terms of their elasticity compared to particle-stabilized systems. So you just look at these scales, they're very different. So now if we take this information and go back to this Gibbs elasticity criterion and look at the criterion, which is kappa S being larger than gamma over 2, and then have this line of gamma over 2, and then put all our data here, what we see is that for the particle stabilized case, we have satisfied the Gibbs elasticity criterion. And for surfactant stabilized case, the criterion is not satisfied, which explains why the bubbles are coarsening in the surfactant stabilized case as shown here, and they're very stable for particle stabilized case. So this is great. So we have basically explained why particles are better stabilizers in this case than surfactants. But we didn't stop there. We wanted to learn more about the differences between these two systems, especially between the two particles. Okay, the overall foam height is the same for the two particles, but is that all, or is there more to be learned? And are they different in terms of the microstructure at the interface. And again, when we looked at them under trough, the capillary interactions were showing up earlier on for the rough particles. So to do that, we have these liquid content modules. What we do, we put these in the dispersion before we start the foaming. What it does is just simply measures the conductance across the foam. If you have more water, higher conductance, so higher volume fraction of the liquid. If you have more bubbles, lower conductance, and higher volume fraction of bubbles. So from there, you can get information about volume fraction of each two phases. And this can be very helpful. So once you start the foaming, the particles are very spherical in shape. The osmotic pressure is 0. And these particles or the bubbles are spherical. They are not sustaining any contact forces. As the liquid starts to drain, these bubbles start to come closer. And at some point, they're going to jam, and they're going to also deform due to the contact forces into these polyhedral shapes, which results in higher interfacial areas. So now the osmotic pressure is larger than 0. So as the foam is draining, the liquid drainage can tell us something about the osmotic pressure in the system that's developing. So if I go back to the data, here is the system of surfactants and how it's basically reducing the foam height as a function of time. And here is the osmotic pressure data for the 3 sensors. Sensor 1 is the closest to the bottom. As you can see, the liquid is draining so fast. The sensor 3, which is right here, is losing data very early on, followed by sensor 2, followed by sensor 1. So this foam is draining and it's destabilizing over a very short period of 1 hour. If you look at the particle stabilized one in this case, as you can see, they're very different. Even though the height is the same, the sensors data is very different. For the round particles, it's more staggered, meaning that the liquid is draining from top to bottom. For the rough particles, all 3 sensors, the data are pretty much overlapping. So even though the overall foam height is the same for both particles, the microstructure and texture of the foam is different for the 2 particle types. So how do we explain this? We can again go back to the rheology, in this case, shear rheology, because we want to understand the effect of liquid drainage and also the impact of particles at the interface on the drainage. So what do we do here? We basically put a ring at the interface and we shear the interface to look at the response of that monolayer. And again, we can effectively change the surface coverage because we have integrated this setup with a language trough, so we can compress, increase the surface coverage, shear the interface, look at the data, and then compress again, increase the surface coverage, shear, and repeat. Okay, so this is the kind of data you would get as a function of packing fraction. The colors are getting darker and darker as we increase the packing fraction. So on the top, you're looking at the elastic modulus. On the bottom, you're looking at the viscous modulus. And then left-hand side is the round particles, right-hand side are the rough particles. So you quickly notice that elastic modulus is higher than viscous modulus. So these are very elastic networks. And the round particles have a higher G prime than rough particles because, again, these are not hard spheres, but rather they're aggregate structures. And we have done AFM, and at some points they might be smaller than 250. They could be even as smaller as thin as 100 nanometers. So this explains why their elastic modulus is slightly lower. But what is interesting is looking at their yield, right? So how much strain can I apply to this network before this network starts to flow? And you can get that information by looking at the strain amplitude oscillations and look at a run of changing the strain and look at how the monolayer responds and what is the response of that monolayer from a plateau value of G prime, meaning that the network is not perturbed or broken, up to the point where the network is now flowing, and that's why the G prime goes down. So from that cross section, we can actually get the strain value at yield. So how much strain we can apply before the network yields. And very interesting information here in relation to that arresting of the liquid drainage is the fact that the rough particles actually, for a similar surface pressures, show higher yield of strain. So they can actually prevent or resist the applied deformations to a larger degree compared to round particles. And this is what we think can be used to explain why they are very good at arresting liquid drainage compared to these round particles, because they have a higher yield of strain. So once the liquid is draining, it has to overcome a higher yield strain in order to break the network and flow through. Okay, so in summary, I hope I showed you just a little bit of what we do on the space of Pickering Foams. In this talk today, I only focused on silica particles, and we showed how the particle wettability is important for trapping them at the interface. But even though we can stabilize foams using particles, each particle and their attributes are going to affect the texture of the foam differently. So there is definitely a correlation between the stability of the foam and also the properties you get at the interfaces using these particles. And these results were published a few months ago. Here's a barcode if you're interested in learning more about the details of this work. And I focused only on roughness, right? Of course, this is a very complex phenomenon. Multi-level attributes can come into play. For example, we work on anisotropic particles. We have collaboration on softness. I didn't talk at all about solution properties, right? So if you think about the charged particles, depending on the pH, you can have different charge on the particles, and therefore the interactions are going to be different as the particles are going to come closer to each other. Electrolytes, again, the same. And one very interesting factor is presence of surfactants. So oftentimes surfactants are used to basically absorb on the particle surface and change the properties. What we are working on is even similarly charged particles and surfactants, and we are seeing very interesting behavior where actually the particle and surfactant mixture is very different than either of those, and they're working synergistically together, even though they are both negatively charged in this case. So if you're interested, I can tell you some more about this work, which is in progress. But I just want to close and say, I hope I showed you some of the work we are doing in the phases space of fundamental interfacial phenomena and its relation to energy applications. We also work on a space where we're looking at these interfacial phenomena and its association with human health in terms of spreading of mucin solutions on surfaces, because again, they're surface active as well. So their presence at interfaces can affect the spreading and wetting behavior. So just the message here is that all of these fundamental problems can have applications in many different sectors altogether. So with that, I would like to thank the funding sources and my students that did the work. Again, thank you for the invitation, and I would be happy to take any questions.